What's going on, everybody? It's Mr. Gustin. We're back in the physics classroom. Today, we're talking about satellites. Not just any satellite. We're calling these things geosynchronous satellites. So satellites are objects that orbit the Earth. They orbit the Earth in an elliptical, roughly circular, mostly elliptical. We can average out that ellipse into a circular path. But they orbit our Earth at different altitudes, and they move at different speeds relative to their altitudes. Now, if we think about how we get something into orbit, we know we have to launch it from the Earth up into the orbit. We have to launch it with enough speed for it to leave the atmosphere, or at least get into the upper atmosphere, where there's less air. Air resistance is an actual part of physics and a real thing, so we have to make sure our satellites leave the lower atmosphere, or at least enter the upper atmosphere, or leave the atmosphere, so that there's not so much drag force, so that these satellites can continue to orbit without losing a bunch of energy and crashing into our planet. So today we're talking about geosynchronous satellites, and our particular question we're going to try to answer today is, what is the orbital speed of a geosynchronous satellite? That weird word geosynchronous is the crux of this problem. So the word geosynchronous, if we break it apart, geo means Earth, Chronos at the end means time, and syn in the middle means like same. So basically, I'm looking for a satellite that the Earth and time orbit in the same way. So a satellite, typically, if we think about the ISS, or the International Space Station, it's at a pretty low orbit, low Earth orbit, or LEO as NASA calls it, and it orbits the Earth around an axis, or around somewhere, a latitude or a longitude. It actually moves pretty all over the Earth, but it does so in about 90 minutes. It's pretty quick. It does not take a very long time for it to move around the globe. So naturally, the satellite is moving faster than the Earth is rotating, right? It's moving around the Earth every 90 minutes. It's every hour and a half. It makes one revolution around the planet. So it's moving much, much, much faster than our planet is moving itself, right? Our planet spins on its axis roughly every 24 hours. That's how it works. So for a geosynchronous satellite, what that means is that a geosynchronous satellite is actually stationed somewhere above our planet. So for example, we live right here in Illinois. It's hard to see where I am, but we live in Illinois, right there, right by Lake Michigan. We live right there. So a geosynchronous satellite is a satellite that would examine or stay directly above a certain point at all times. So essentially what we're saying is, where does a satellite need to be, and what is the speed of it if it's going to move with the Earth? So its speed is going to make it such that it rotates around the Earth with the same speed that the Earth moves. Geosynchronous. It's going to stay in the same geographic location and make its orbital path in the same time. Now, there's some weird things around that, but let's go ahead and discuss that. We'll calculate that. So a geosynchronous satellite means it's going to stay above a certain spot on my Earth the entire time. It's not going to fly around like the ISS. It's not in a low Earth orbit. It's actually in a very high Earth orbit. So high that we have to actually look up in Google. I had to Google what the altitude of geosynchronous satellites are. So I'm going to write that on the board. A geosynchronous satellite typically has an altitude above the Earth equal to roughly 35,780 kilometers. Or, 1, 2, 3, we would say it's 35780 meters. 1, 2, 3, 1, 2, 3. 35 million meters, or 35,000 kilometers. This is the altitude. All right, now we also have the mass of the Earth. We know this to be 5.972 times 10 to the 24th kilograms. And we know that the Earth's radius, or the radius of the Earth, is equal to 6378.1 kilometers, or 6378100, 6,378,100 meters. These are some important values I need to know. Now we can go ahead and start thinking about the satellite. Let's go ahead and draw our picture. I've got the Earth the Earth has a satellite somewhere way out here making a roughly circular orbit. The only reason it makes that orbit is because it is in Earth's gravitational field. If it makes this circle, we have a radius r of the Earth plus the altitude of the satellite. This is the difference in position. So I see this here. Now, if it is making a roughly circular path, that must mean that Fg is a centripetal force. It's taking this circular path around the planet. Okay? And if that's true, I can expand this and say, well, Fg, when I'm not at the surface of the planet, is equal to mama g, mass of the Earth, mass of the satellite, divided by the total distance between two objects squared. And this is equal to the mass of the satellite times the orbital speed of the satellite divided by its own radius, mv squared over r. This is my centripetal force equation. And then this is my expanded gravitational, my universal law of gravity. So as I go to solve this, I see some things start to drop out. The mass of the satellite is not going to dictate how fast I orbit because it's not about, like the acceleration of the satellite is not dictated by its mass, just like objects on this Earth's speed when they're in free fall are not dictated by mass. Now, one radius drops out from each section, and I'm just looking for v squared. I'm just looking for how fast this thing moves around the planet. All right, so let's expand this more or simplify this. Mass of the Earth over r equals v squared over nothing. So my speed is actually going to be equal to the square root of g and e over r, and that's going to be my v orbital. Okay? This is one solution. I'll let you calculate that, but this is actually always true. The orbital speed of something that moves around our planet is equal to this. This equation is known as orbital speed. So if I'm thinking about how do I know how fast something needs to move in order for it to stay in orbit, this is a derived expression that will always tell us the answer. Now, two things here remain the same. Mama g is the universal gravitational constant. This stays the same no matter what. The mass of the Earth, barring any major cataclysmic events, this thing stays the same. And this r value here is just the distance above the center of the Earth something is. So if you want to figure out how fast something needs to move to orbit, and you have raised yourself high enough in Earth's atmosphere where there's minimal air resistance, that's kind of key here. If there's minimum air resistance removing energy from the satellites, then this will dictate the orbital speed of an object. Now, we didn't really rely on this geosynchronous thing. Let's look at a different solution. There's a second solution to this problem. I wonder how fast this thing is going if I didn't use forces. So let's check it out. I'm also looking for, I have a different equation for speed, right? Speed is also equal to the circumference over the period. This is also true. All right, so I don't exactly know this answer, right? But I can plug some things in, right? So this is also another solution. This is, instead of using forces, I can just jump right to speed. And because it's geosynchronous, I know some information. The first thing I know is I know that r value. I know that if I look at my picture, the r value of this orbit is the radius of the Earth plus the altitude of a geosynchronous satellite that I got off Google. I also know that if it's going to be geosynchronous, that means that the object, the satellite, is going to orbit the Earth or not move relative to the Earth. So how long does it take this globe to rotate once around to make one circular path, or so that this object makes the circular path while the Earth rotates beneath it? It's going to take roughly 24 hours. This period here is 24 hours roughly, right? And it's not, right? 24 hours is not an exact number. That's why we see leap years and stuff. But 24 hours is this period. So I have to convert 24 hours into seconds. So 24 hours, 60 minutes in an hour, 60 seconds in a minute. I make that conversion over here, and I can end up with V being equal to 2 pi times the radius of the Earth plus the altitude divided by the period, and then in parentheses, in seconds. and I challenge you. I challenge you to try both methods. I challenge you to see, are both of these equal? But in both cases, because we're dealing with geosynchronous satellites, I kind of secretly know the period of the orbit for this satellite. If it wasn't geosynchronous, the second method wouldn't work. The first method would have to be used, and that's okay, because like I said, this is known as orbital speed, or our equation for orbital speed. Okay? Give both a shot, give it a try, solve your problems on orbits. There's a simulation, you can give it a try as well. If you have questions, as always, drop it in the comments, ask me in class, but until then, see ya!